Welcome. In this session, we are going to round out by talking about the remaining two rules of integration in our original list of basic rules. One of them was the antiderivative of 1 over x. Remember, the power rule doesn't work for 1 over x. So we know a function whose derivative is 1 over x, namely logarithm of x. But the problem with using that as our formula is the mismatch in the domains. The domain of 1 over x consists of all non-zero numbers, positive and negative, whereas ln of x is defined only for positive numbers. So before we talk about the formula, let's do a differentiation problem we have done before in section 12.1, which is to differentiate ln of a constant times x. So we will use our old general approach for differentiating ln. Take the reciprocal of the inside. So in this problem, I would have 1 over ax multiplied by the derivative of the inside. Inside is the constant factor a times x. Its derivative with respect to x is a. And 1 over ax times a is 1 over x. The a's cancel. This is somewhat surprising at first glance. I said that all antiderivatives will differ by a constant. But it looks like 1 over x has lots of antiderivatives, ln of a times x, which don't look like they differ by a constant. But it's partly only illusory because if a is positive, I can split up ln of ax. Logarithm of a product is sum of the logarithms. So ln of a times x is ln of a plus ln of x. Of course, this works only if both a and x are positive. So in this case, there is nothing surprising. The different antiderivatives do differ by a constant. It just involves logarithms. But what if a is negative? Well, let's take the simplest negative number, negative 1. ln of negative x also has antiderivative 1 over x. Now, when I said all antiderivatives differ by a constant, I was leaving out an important qualification, because in practice it doesn't matter as much. So if you take two functions whose domain is the same interval and whose derivatives are equal, then they differ by a constant. But if you have two functions like ln of x and ln of negative x, whose domains are completely separate, domain of ln of x consists of all positive numbers, domain of ln of negative x consists of all negative numbers, then that's no longer true. But we can get an antiderivative for the combined intervals. So you take the domain consisting of the two separate intervals, then you just take the function which is defined to be one or the other depending on the interval. That will be an antiderivative for the original function over the combination of the intervals. An antiderivative of 1 over x, which works for both positive and negative numbers, is the function defined as ln of x if x is positive, ln of the opposite of x if x is negative. We can write this in more compact form as ln of absolute value of x, because absolute value of x is x if x is positive, opposite of x is if x is negative. Absolute value of x is x if x is positive. Absolute value of x is the opposite of x if x is negative, which means ln of absolute value of x is a function defined whenever x is not 0 and whose derivative is 1 over x for all non-zero x. So we get the general antiderivative of 1 over x as ln of absolute value of x plus c with matched domains. So this gives us that formula. What about exponential functions? Of course, for e power x, we know an antiderivative is e power x. What if I have some other base? Let's look at 2 power x. We know that if I differentiate 2 power x, I get the exponential 2 power x and also a factor of ln of the base of the exponential. In this example, ln of 2. I want to divide off ln of 2, which I can do since ln of 2 is a constant factor. So I can divide before I differentiate, the effect will be the same. So an antiderivative of 2 power x is 2 power x over ln of 2, and with the plus c I get the general antiderivative. We can push this a little bit further. If I have a constant factor in the exponent, then when I differentiate, I get the constant factor in the exponent, the coefficient in the exponent as an additional factor. So I have to divide it off. So if you follow through all the details in calculation, we get the formula that an antiderivative of a power kx is a power kx over k ln of a, which gives us our next formula. A particular case of this is the one that we use most often, because in calculus, we preferentially write exponentials with base e. The general antiderivative of e power kx is e power kx over k plus the constant of integration. In textbooks, they generally give the formula for e power x and handle this case by using the method of substitution, which we'll talk about in section 4. But in a lot of applications, we get e to the power constant times the variable so often, it's worthwhile to formulate this general rule. So in my notes, I will use this formula rather than the special formula on the method of substitution. And you can also do the same on tests. This concludes our look at the basic rules of